Hello, and welcome to Business Calculus Limits at Infinity. The infinity symbol can be used to represent a domain value which increases without bound. We say that x approaches infinity, meaning that x is increasing without bound, and hence going farther and farther right on the real number line. We say that x approaches negative infinity, meaning the same thing in the opposite sense. X is decreasing without bound, moving as far as it can to the left on the real number line. This allows us to examine the behavior of power functions, x to the p power and 1 over x to the p power for some real positive p, in the limit as x approaches infinity and also in the limit as x approaches negative infinity. We see that the power function x to the p in the limit at infinity is equal to infinity, and the limit of the function 1 over x to the p in the limit as x approaches infinity is equal to 0. We demonstrate that with a pair of graphs. We see here in red that the function f equals x squared is increasing very, very quickly as we approach infinity in the positive direction, and the function very quickly shoots off and will forever be unbounded. We also look at our function g, 1 over x squared, in blue, and see that as we go towards positive infinity in the x direction, that the function itself decreases very quickly towards 0, approaching the horizontal asymptote y equals 0. This allows us to state a theorem about how power functions behave at infinity. We have, if p is a real positive number and k is any non-zero real constant, then the limit as x approaches negative infinity of k divided by x to the p power is 0, and the limit as x approaches positive infinity of k divided by x to the p power is equal to 0. We also have expressions for our power function x to the p. We say that the limit as x approaches negative infinity of k times x to the p power is equal to positive or negative infinity, and the limit as x approaches infinity of k times x to the p power is equal to positive or negative infinity, provided that x to the p is a real number when x is negative. What we don't want to be doing is taking powers We have the following theorem about the limits of power functions at infinity. If p is a real positive number and k is any non-zero real constant, then the limit as x approaches negative infinity of k divided by x to the p power is equal to 0. And the limit as x approaches positive infinity of k divided by x to the p is equal to 0. Also, we have that the limit as x approaches negative infinity of k times x to the p is equal to positive or negative infinity, and the limit as x approaches infinity of k times x to the p power is equal to positive or negative infinity, provided that x to the p is a real number when x is negative. We don't want to be doing something like taking the square root of a negative number, which results in complex values, which is beyond the scope of this evaluation. The limits in property 3 and property 4 are going to be positive or negative depending on the particular values of k and p. Let's look at an example. Let's take the polynomial function 2 times x cubed minus x squared minus 7x plus 3 and determine the limit of p of x as x approaches positive infinity and as x approaches negative infinity. We want to use properties 1 and 2 from the previous slide because the limit as x approaches infinity of 1 over x to the p is equal to 0, which will make our polynomial much easier to work with. In order to be able to exploit this property, we factor out 2x cubed from every term in our polynomial, leaving us with 2x cubed times 1 minus 1 over 2x minus 7 over 2x squared plus 3 over 2x cubed. And we evaluate the limit of the product. Looking at just the right-hand factor of our product from the previous page, we see that in the limit as x approaches infinity, we have 1 minus 0 plus 0 equals 1. Assuming that we're looking at a very large value of x, this is approximately equal to 1. This means that our polynomial function, which we have written down here in its factored form, is approximately equal to 2x cubed whenever x is a very large value. This allows us to say that the limit as x approaches infinity of p of x is equal to the limit as x approaches infinity of 2x cubed. The largest degree term of the polynomial is infinity. And likewise, the limit as x approaches negative infinity of p of x goes as the limit as x approaches negative infinity of 2x cubed is equal to negative infinity. If p of x is a polynomial of degree n, we have the following theorem. We express p of x as a generic polynomial of p of n, where the a sub n minus 1 terms represent the coefficients of the polynomial. Then we have the limit as x approaches infinity of p of x goes as the largest degree term, a n x to the n power. Likewise for the limit at negative infinity. The choice between positive or negative infinity depends on the particular value of a sub n and n. What we would like to do now is determine the end behavior of the following functions using our previous theorem. Looking at our first example, f of x, we're going to look at the limit as x approaches positive infinity of 4x cubed minus 400x squared. Now what we want to do is identify the largest degree term. So all we're interested in looking at right now are how big these exponents are. And we see that 3 is the larger of these two exponents. This tells us that the limit of this whole function at infinity is equal to the limit of just 4x cubed. Now, x at infinity is a very large positive number. A very large positive number cubed is also positive, and we multiply it times a positive constant, 4, which tells us that this limit is equal to infinity. Next, we are going to look at the limit as x approaches negative infinity of our same function. Again, we know from our theorem on the previous page that the behavior of this function is dominated by its largest degree term. So the limit of all of f of x is equal to the limit of 4x cubed. And when x approaches negative infinity, it is a very large negative number. A very large negative number cubed is also negative. And we multiply it times a positive constant 4, which tells us that this result is negative infinity. All right, let's look at number 2. Again, we want to check the limits as x approaches negative infinity and positive infinity. We'll do positive infinity first. We copy down our function, the limit as x approaches infinity of 3x cubed minus 400x to the fourth, and look once again at the exponents of the function. We identify that 4 is bigger than 3, so the term involving the largest exponent is going to be the one that dominates the behavior of the limit near infinity. So this limit is going to go as the limit as x approaches infinity of negative 400x to the fourth. And now we look at the particular values at hand. 4 is an even power, and an even power to any number x is going to be an even value, or a positive value, and a positive value times the negative value 400, negative 400, is going to give us negative infinity. We're going to have a very large positive number times a negative number, which is ultimately negative. Now we look at the limit as x approaches negative infinity of our same function. We know from our previous determination that this limit is dominated by the largest degree term. And now we evaluate the limit based on this information. X is being raised to the fourth power. Because 4 is even, x to the fourth is always going to be positive. And negative 400 times a positive number is a very large negative number. So we say that this limit is also equal to negative infinity. All right? And to finish up, I would like you to determine the left and right end behavior of the following two polynomials. F of x equals 150x squared minus 2x to the fifth, and g of x equals 150x to the sixth minus 2x to the fifth power. Here are your potential responses, keeping in mind that you're looking at the left and then right end behavior of f of x, then g of x. Thank you very much for listening, and I will see you next time.